So here we come to the topic of the Boolean algebra. I think you all should have the basic knowledge about the binary number system. Then I'm moving forward. The Boolean algebra. What is Boolean algebra? A Boolean algebra function is an algebraic expression formed using binary constants. What is binary constants? That is 1 or 0. It may consist of binary variables. That is, I may give a variable of a or b. It may consist the value of 0. It may consist the value of 1. Only 0 and 1, nothing else. And also the some basic logical functions like AND function, OR function, NOT function, etc. I'm coming to the points. What is AND function? What is OR? What is NOT? So these are the logical functions. So a Boolean algebra is an algebraic expression which are formed using binary constant, binary variables, and logical functions like AND, OR, and NOT. AND or NOT are the basic functions. Okay. So what is AND function? AND means, suppose I have two variables, that is A and B. The output expression is like A dot B. Y is equals to A dot B. It is also basically known as binary multiplication. Here you can see from the truth table. What is truth table? Truth table gives the input-output relations. Suppose there are two variables, A and B. It may be more than two, but as per basic, I'm teaching you the at most basic rules. That is, if I have two inputs, so what will be the total number of combinations? Total number of combinations will be 2 to the power number of variables. So here is the number of variables 2. So total number of combination will be 2 square equals to 4. What are these 4 combinations? These are 0, 0, 0, 1, 1, 0, and 1, 1. So if I multiply these numbers, y equals to a dot b, and the basic representation of AND gate is like that. This one. These are the input side A and B, and I have an output of y which is equals to a in a dot b. So here you can see if both the inputs are high, then the output is also high. High means 1, low means 0. If both the inputs are 1, only at that time the output will be 1. Otherwise, all the output will be 0. If at least one input is 0, then the output is 0. All the inputs are high, then the output is also high. This is the basic logical AND function. Now I am coming to OR function. In that case, the output y will be equals to a plus b, and the basic gate representation is like that. So in that case, if at least one input is 1, then all the output will be 1, and when all the inputs are 0, output is also will be 0. This is the basic OR function. I have to choose between A or B. I always will choose the higher part. That is why low or high, output will be high. High or low, output will be high. If you have to choose between two high, output always will be high. If we have to choose the output between two low, the output will always be low. So y equals to a plus b. If at least one input is high, output will be high. If all the inputs are low, output will also be low. And logical NOT or complement or inversion is just opposite. It has one input and one output. It may be expressed as y equals to a bar or a complement or a dashed. If the input is 0, output will be 1. If the input is 1, output will be 0. Basically, it acts as inverter. It will be the logical inverse operation actually. This is the function of logical NOT operation. Well, now I am going to some Boolean algebra rules. I've already told about the OR operation. At least one input is 1, output will be 1. All the inputs 0, output will be 0. I've also taught about the AND, all input 1, output will be 1, otherwise it will be 0, at least 1 0, output will be 0. Now, from this, we can conclude A plus A bar, that is 1 plus 0 or 0 plus 1. What is that output? Is always 1. So A plus A bar will be 1. A plus 0 is always 0. Suppose something plus 0 is equals to something in that case, and in that third case 1 plus 0 is 1, so A plus 0 is A. And when I am look at this second one and this fourth one, A plus 1, that is 0 plus 1 1, 1 plus 1 1, so 1 plus anything will be equals to 1, and A plus A equals to 1, that 0 plus 0 is 0, 1 plus 1 is 1, so A plus A will be A. Similarly, from this AND function we can conclude A dot 0 equals to 0. If I multiply or make an AND operation of if I make an AND operation of 0 and another variable, it will be 0. If I make AND operation between same variable, the output will be that one. A dot A equals to A. A dot 1 will also be A, and A dot A bar, that is the complement, and the variable AND function will result in 0 output. And complement of complement will be A. These are some general rules. These are the properties. Properties of Boolean algebra: cumulative property A plus B equals to B plus A dot B equals to B dot A. These are the cumulative. What is associative? That is A plus B plus C equals to A plus B in the bracket plus C. Similarly, I can have it in the dot function, that is AND operation. It is very important part is distributive property, that is A plus B C equals to A plus B into A plus C. It will be shown later as we will further move to some Boolean math. A plus AB, these are also are very important. A plus AB equals to A into A plus B equals to A plus A bar B equals to A plus B, and A dot A bar plus B equals to AB. And finally, consensus laws. AB plus A bar C plus BC equals to AB plus A bar C. Not the BC part will be rejected. Same thing will be done in the next part, that is A plus B dot A bar C dot B plus C. That B plus C part will be neglected. And this De Morgan's theorem, it is a very much important part for throughout digital electronics study. De Morgan's theory states two laws, that is, the first theorem states that the complement of a product is equal to the sum of the complements, that is A dot B whole bar equals to A bar plus B bar. That means the complement of a multiplication is the summation of complemented inputs. Similarly, second theory states that the complement of a sum is equal to the product of complements, that is A plus B whole bar equals to A bar dot B bar. These are the De Morgan's theorem, and this is very much important. Again, I am saying these are the very much important theorem. It is very much helpful for throughout digital electronics and throughout your curriculum study. Now, these are some simplifications. This is also very important. You have to know the simplification rules. You have to know the theorems. Then you can simplify any Boolean algebraic expression. If I can simplify Boolean algebraic expression in the shortest form, then the circuit to implement that expression will also be very small, and that is the target of an electronic engineer, that I will use the lesser number of the less number of components, and I will have better output, same output, so the efficiency will be high. So let's carry on. The first simplification, just to simplify the expression, A plus A dot B bar plus A bar dot B. This expression I have to simplify. This one. So what I have done in the first line, I have just taken A common from first two term. So if I take a common, it will be 1 plus b bar. Okay. And from the previous theories, 1 plus any variable will all equal to 1. So this part will become 1. So 1 into a. I'm just coming to the theorems. This one, a plus 1 equals to 1. So if I add 1 with any Boolean variable, it will give 1. And if I multiply 1 with any Boolean variable, it will give the same output, that is a dot 1 will be equals to a. So here 1 plus something will be equals to 1, and this one is multiplied with a, so it will give a, that is a plus a bar b. Now I am just coming to that theorem. This is distributive property, a plus bc equals to a plus b into a plus c. So using that theorem, I can write a plus a bar b equals to a plus a bar into a plus b. From here to here. Now a plus a bar. What is a plus a bar? A plus a bar will always be 1 from the theorems. So this will become 1. So 1 into a plus b will give me the answer of a plus b. So this expression a plus a dot b bar plus a bar dot b has become very shortest term, that is a plus b. So I can implement it just by an OR gate, nothing else. I do not need any NOT gate, or I do not need any AND gate or something else. I just need a OR gate. Similarly, just another one, simplification of that AB bar plus ABC whole bar plus A into B plus AB bar whole bar. So what we have done, from distributive property, that B plus AB bar become B plus A into B plus B bar, that B plus B bar is equals to 1. So it is 1 into something will be that one. So B plus B bar is eliminated. Now what I have done, I have multiplied that one. AB plus A into A. A into A will give me only A. That why? Now 1 into 1 equals to 1 and 0 into 0 equals to 0. So A into A will become A. Now I am taking again A common. So it will become B plus 1. So 1 plus something means it will become 1. 1 into A means only A. Well, now coming to this part. Now I have multiplied this one, AB bar plus AC. So using De Morgan's theorem, what De Morgan's theorem states, A plus B whole bar equals to A bar dot B bar. So this one plus this one whole bar will become this AB bar into AB bar whole bar into AC bar. So this is the second, I have applied the second theorem of the De Morgan's theorem. Now again I will use the first theorem of the De Morgan's law, that is AB bar whole bar become A bar plus B, and it will become A bar plus C bar, just like that, this line. Now again coming to the distributive one, the reverse of distributive actually is absorption property. A bar plus B into A bar plus C bar will become, from absorption property, A bar plus B C bar. And again just simplify this one, A bar plus A always become 1. So 1 plus something will become 1. 1 complement is equals to 0. This answer is 0. So no need of any gate to derive that expression, to implement this expression. Only a ground pin, that will become 0. That is, overall output will always be 0. No need to implement any circuit to implement this bigger complex expression. All it becomes is 0. That is why it is very important for you to simplify these expressions, to know the Boolean algebra basics rules, so you can study digital electronics very carefully throughout your curriculum throughout your working profession. No one knows that you can become a teacher again in future. So I'm coming to another problem, that is y equals to ab bar plus a bar b into c. Just I've applied the second theorem of the Boolean, second theorem of the De Morgan's theorem, and it has become not. I have just expressed b as b double bar. Complement of complement, it becomes the same. So I can write b double bar in place of b. Now I've applied the first theorem of the De Morgan's one, that is a bar plus b bar equals to ab whole bar. So in that case, a b bar whole bar. Now distributive property, ab bar plus ab bar plus ab bar complement. It will be complement. Sorry for the mistake in that case. And the next part will be ab bar plus c. So this part will become 1 because I'm adding the same thing with the complement. That is a plus a bar equals to 1. So it will become 1. 1 into something is that. So it will become the final output ab bar plus c. Again, I'm mentioning it will be a bar in here. Similarly, in that case, find the complement of the expression. So complement means y is given. I have to check out what is y bar. So I have given a whole complement, and you applied De Morgan's theorem, the second one, that is a plus b whole bar equals to a bar dot b bar, which states the complement of a sum is equal to the product of complement. So complement of sum has become the product of complements. In the second line, you can see all the all the terms have a complement here. That is the second law of De Morgan's theorem. And now I have applied the first theorem of De Morgan's one, that is ABC whole bar equals to a bar plus b bar plus c bar. That is the complement of product is equal to sum of the complements. So it is done for all the four ones. Now you can see from the first two, a bar plus b bar and a bar plus b bar. So I can, if I imagine these two as the same variable, which is added first with p bar and then added with p and dot, they are multiplied. So from distributive property, what distributive property says, that is a plus bc equals to a plus b into a plus c, or from absorption, a plus b into a plus c equals to a plus bc. So if a bar plus b bar is a single component plus b bar into c. So c bar is equals to 0. So it becomes a bar plus b bar. And same case here, a plus b bar, a plus b bar is taken as one variable, and b and b bar, they are added with b and b bar, and they are dot product between, they have dot between them, that is the AND operation. So b plus b dot b bar is equals to 0. It becomes a plus b bar. So this is the ultimate final expression of the complement of y. So y complement will be a bar plus b bar into a plus b bar. So that's how you can solve the Boolean algebra. You have to just remember these laws which I told you just a while ago. The De Morgan's theorem consists from services laws, absorption property, distributive property, associative property, cumulative property, and the Boolean addition and Boolean multiplication and complement function. That's it for the Boolean algebra. Now I am coming to the form of sum of product and product of sum. Any Boolean algebra can be expressed as sum of product and product of sum, like that. These are the sum, that is plus sign, and sum of what? You can see these are the product of two variables. So if I express like this, it will be the sum of The variable by which it is expressed, these are called min term, and this is the product of sum, that is product of what? Two variables which are summated between them, and the term by which QS, that product of sum, is expressed are called max term. So these are min term, these are max term. So now just see the expression one, y equals to a plus b bar c. Just what to express, my objective is to express this particular function in sum of product and product of sum form. So first sum of product. Now y equals to a plus b bar c. I have to, in the first term a there is no b no c, in the second term there is no a. So I first have to convert all the terms in terms of a b c. All the terms should consist of a b c. First I have learned in Boolean algebra how to minimize the expressions. Now I have to learn how to maximize from shorter term to the longer term. So with A, I have to add B plus B bar and C plus B bar. Why? Because B plus B bar is 1, C plus C bar is 1. And from B bar C, I have to multiply A plus A bar. Which one is absent? I have to just insert them by like that. B plus B bar, C plus C bar, or A plus A bar. Now just multiply them and you will have this expression. And how I have written this M7, M6, M5, M4, M1, I have just told that the way by which sum of product is expressed are called the mean terms. The terms are called mean terms, and this ABC is the seventh term, that is M7. Why? Because there is no bar, so if I imagine ABC are equals to 1, so 111 gives you 7 in decimal. 110, C is bar, so 110 will give 6 in decimal. 101 will give 5, 100 will give 4, 101 will again. So two terms are same, A B bar C and A B bar C. It will be termed as 1, not 2. So I will have only one M5, not two M5. And now, and the A bar, B bar, C. A bar, B bar, C is 1, sorry, 001, that is the M1, the first one. It will be 1, 2, that one. Sorry for the interrupt. Something has happened wrong. Just stop the share, the screen share. Sorry. My screen share is paused. Why? Sorry for some interruption was there due to technical fault. So we were here to discuss the how a function can be expressed in terms of SOP and POS form. So in SOP form, we have learned how to write the mean term. So it is the summation of 1, 4, 5th, 6th, and 7th term. As you can see, the three variables are there. So there are eight terms, that is 0 to 7. So not the 0th to 7th term are the 8 terms in that case. So it can be expressed as the summation of first, fourth, fifth, sixth, and seventh term. Similarly, in POS form, first apply the distributive property. So a plus b bar c becomes a plus b bar into a plus c. This is the distributive property. So first in the first term c is absent and the second term d is absent. So a plus b bar can be expressed as a plus b bar plus c bar, and in that case a plus c can be expressed as a plus b bar plus c. Now again I am applying the distributive property and it becomes a plus b bar plus c and a plus b bar plus c bar. Similarly, the second term is also expressed like that. Now the first term and the fourth term is same, so it will be regarded as only one term and it becomes a plus b bar plus c into a plus b bar plus c bar into a plus b plus c. In the mean term, we are assuming a, b, c as 1 and the complementary terms are as 0. In that case, the complementary term will be regarded as 1 and the a, b, c will be termed as 0. So 0, 0, 0 becomes 0 in decimal, 0, 1, 1 will become 3 in decimal, 0, 1, 0 becomes 2 in decimal. So 0th term, second term, and third term. So y is the product of 0th term, second term, and third term. These are the max term, and the summation symbol is used for SOV form and pi is used for QS form. This is the multiplication. Now today's last topic is Carnot map, and basically it is known as K-map. It's very much important and essential part for any digital electronic circuit for an electronics engineer. First, we have to know the truth table. From truth table, we can specify what our target is, what we will give the input, and what output we will get. So according to, we have to design it. So first step from truth table is to develop a Carnot map. From Carnot map, we can develop an equation by which we can use the minimum number of components to design a circuit. So that is why K-map is very essential. So these are some figures of Carnot map, how Carnot map is built. This is two variable Carnot map as earlier discussed. In two variable there are for two variables there are four combinations, that is 0 0 0 1 1 0 1 1. So this one is 0 0, that is the output will be written in that. This is the first term 0 1, that is 1 0, and this is 1 1, that is third. For three variables there will be total number of cell will be 8. For three variable 2 to the power 3 is equals to 8, and the K-map is written like that. A will vary from 0 to 1 and PCR will have 4 combinations, total 8 combinations, and it is written as 0 0 0 1 1 1 1 0, not 1 0 1 1 because I cannot vary two variables at same time. So what are the terms what are the terms that represents a cell, that is 0th term, first term in that cell, second in that, third in that cell, fourth in that cell, fifth in that one, sixth in that, and finally seventh. Similarly, for four variables, 2 to the power 4 equals to 16, so number of cell will be 16, and same for the combinations will be, that is 0 0 0 1 1 1 and 1 0, and in the column side is also same. So that's how the cells are numbered, that is 0 1 2 3 4 5 6 7, and coming to the last row, that is 8 9 10 11 10, and here 12 13 15 and 14. Now just go down to this one as an example how K-map is solved. So you can see this is summation symbol is used. So this is product, sum of product from, that is SOP form, and the terms are 7 9 10 11 12 13 14 and 15th term. So 15, 0 to 15 means total 16 term, and 4 variables are there, so we have to use the 4 variable K-map like that. So just I have numbered the cells, I have taken the variables, and now just put 1 in place of 7th cell, that is this one, 9th cell here, then comes to 10th, then 11th, then 12th, 13, 14, and 15, and others having an output of 0. Now we have to pair. How can we pair this one? Maximum number of one that we can take, and it must be a power of 2, just like this one. My first preference will be how many. If there is 16 number of ones, you have to pair this 16 number of ones. Then we have to look for 8 number of ones. Then we have to look for 4 number of ones. Then 2. Then only a single one. So in that case, first we have got this row that has 4 number of ones. This is a pair, and in that particular pair, which one is constant? This part, AB. You can see C0, C0, and C1. So C is varying, D is also varying. So only A and B is not varying. So this term is expressed as AB. Then again we can see there are another pair of 4 ones. So in that case, A is not varying. A is here 1 and again here 1. And in that case, D is not varying in these two columns. So it is becomes AD. Then another 4 number of ones is there. So again, A is not varying and C is not varying in that particular case. So it becomes AC. And finally, this one is left alone. But I can take these two as pair, maximum number of 1, and it has to be a power of 2. So CD is not varying here, that is 1, 1, and B is not varying and the value is 1, so it becomes BCD. We have to look for the constant terms. If it is 1, then it's no bar. If it is 0, it will give the complemented output. So in that case, y equals to AB plus AD plus BC plus BCD. Now another expression is that y equals to summation of 0 to 5, 7, 8, 9, 10, 11, 12, 13, 14, 15. Again, similarly, we have to put 1 in that particular number frame. And in that case, you can see there is a pair of 8 ones. In that case, A is not varying, that has a value of 1. B is varying, C is D is obviously varying, so it becomes A. Now another, here we can see 4 number of ones. Here B is not varying and D is not varying, so it becomes BD. And we can see the corner one, so you have to fold that one. If we see the corner one, last row, first row, last column, first column, we have to fold it and make it a pair. So these 4 ones are making a pair where B is constant having a value 0, so it becomes B bar, and also D is constant having a value of 0, so it becomes B bar. So B bar, D bar is the expression of that pair. So it becomes A plus BD plus B bar D bar, and that BD plus B bar D bar is the expression of X NOR gate. So Y equals to A plus B X NOR D is my final expression. That's how simplification can be done by using K-Map. Just we have to put the ones in the number cell and make it pair, and by that we have to find the expression. And another special case is there, which is known as don't care condition. There it is, the don't care condition. You can see summation of 1, 3, 7, 11, and 15 is numbered as 1. No problem with that one. But there is a don't care situation in 0, 2, and 5 that is written as D. This one is D, that is the 0th cell, that is second cell, that is D, and the number 5 cell is D, and others are 0. So here it is a cell in the third column, that is 4 ones. So in that case, C and D is not varying, having a value of 1, 1, so it becomes CD. And now another one is left, that is uh, this one. So I could have made this pair like this 1, 1, but I have to take the don't care. So so the circuit become minimum, so the expression become minimum. But once I have taken all the one, I must not take the don't care. In that case, I have taken this one and it's become A bar B bar, but this don't care is left alone because all the ones are done. Don't care means it may be 0 or maybe 1, but we have to make sure that we encircle all the ones, we make the pair with all the ones with the number of don't care we can take. But if all the ones are done, we uh, should not take any don't care situation. So y becomes ct plus a bar b bar. So that's how Boolean algebra can be solved. Boolean algebra can be solved by some theorems. It can be expressed in SOP and POS form, and also Carnot map can be solved like this. And we'll come with more and more videos from how K-Map, all the combinationals and sequential digital circuit is simplified using this K-Map, these rules. That's how electronics become so easy. That's easy with easy. So please subscribe to my channel if you like this video, and don't forget to make comment if there is any problem. Thank you, and that's all for today.